Okay, so let's begin. And this will be the English version of the HGMM learning and tutorials. And in this session, I will introduce you to how to run and profile HGMM algorithm on the CPU and GPU. And this is my short introduction. My name is Haibin Lai, and my major is computer science. I have been research for HPC, machine learning system, and parallel computing for about a year. And when I was in sophomore, that is 1 year ago, I participated in ASC 24 and APAC 24 competition. And after that, I went into the research about the parallel computing. And I have a publication, and you can also view some of my results and research on my Bilibili GitHub, and you can also see my CV. So my journey with supercomputing starts when in the 2023, I participate in the SUSTCSC 23 and Xiandao competition. After that, I learned some of the technique like VTune profiler, OpenMP, MPI, and in 2024, I participated in ASC 24 and learned a lot of things. And I have a good experience in the Shanghai. I think that having competition is very interesting because you can meet with different people. After that, I just come into APAC 2024. And another great experience in Singapore. I also learned a lot knowledge from my teammates and also everyone in Singapore. And I also learned a lot of things like quantitative approach, CSAPP, and other courses. So overall, I think the HPC learning path looks like this. First, you can, for most people, or just for me, I start with HPC learning from one game called Turing Complete. After that, I start to read CSAPP, that is Computer Systems, a Programmer's Perspective. That is a good book. After that, I read the Computer Architecture, a Quantitative Approach. And I learned parallel programming like OpenMP and MPI. After that, in the operating system class, I learned something like something from the textbook, that is OSTEP, Operating System 3Z Pieces, and also other courses like compiler and the network. Well, I think the thing on the right lists some of the technique you should learn from HPC and machine learning systems like the Tensor Core usage and the VTune usage, KVAS, Docker, and some of the virtualization technique. Also, something from network like RDMA or the CHIL and lots of things. And as for today's introduction, I will introduce what is HGEMM. And in the secondly, I will introduce how to use CUDA to write it. The thirdly, I will give an introduction to the profiler that can profile your program. Now, as we learned before, the HGEMM in our linear algebra class, that is matrix multiplication. So you can do a multiplication for two matrices, that is A and B. So here you can like 1, 2, 3, 4 times 5, 6, 7, 8. And for the first row of the result C, that is 19, it is calculated by 1 times 5. Wait, let me get a pen. Yeah, that's 1 times 5 adds 2 times 7. That is 5 add 14, and the result is 19. And the rest of them are the same. Well, the matrix multiplication is a very important operator inside many of the scientific systems. So to learn the HGEMM, we should go back to the history. In 1979, the Professor Jack Dongara, they come out with the idea that we need to propose a linear algebra library that is for this operator. That is, so he proposed basic linear algebra superprograms, subprograms, BLAS. So BLAS is a sophistication that prescribes a set of low-level routines. For example, in 1979, he proposed the BLAS level 1. That is, everything is a vector-vector operations. And the BLAS level 2 is for matrix vector operations, like the matrix times vector. And it proposed like a form like this one, that is y equals a times x plus beta. So by doing that, you can solve some of the problems like solving the linear algebra equation. And the BLAS level Z was proposed in 1990s, that is matrix-matrix multiplication. And inside one of them, the general matrix multiplication becomes one of the basic operator of BLAS level 3. Nowadays, BLAS has become many of the software's fundamentals middleware inside it, like as we learned before, the MATLAB. So MATLAB was built based on the BLAS library. When you like to compute like the tensor or the matrix multiplication, you will use the BLAS library. And also other thing like the WAF. This competition we are going to, one of the software we are going to use in this competition, also like Llama CPP, NumPy, PyTorch. And today we have many of the BLAS library, like the Intel MKL or the CLU BLAS or the AMD HIP, other thing. Now, GEMM's is only an API, and it got many implications from the NVIDIA and the Intel or AMD. But its API looks like this. So first, you need to input A and B to matrix. And also, you need to input a C, that is the output matrix. Then you need to point out the matrix dimensions using M and K. And the relationship between M and K and ABC is shown as following. Now, you can see that the A, for the A's numbers of row, that is M. And for the numbers of columns, that is K. While the rest of them are the same. We only use 3 parameters because we can define a matrix multiplication size only using 3 parameters. If we just like, for example, n times k and n times that is k2, then the results these 2 metrics can't be multiplied. Well, in some of the GEMM's API, we also defined alpha and beta. That is, this GEMM is calculating like C equals alpha A times B plus beta times C. While LDA, LDB, LDC means the leading dimensions we want to include in this presentation. And after HGEMM was introduced, and here we introduced single precision general multiplication, matrix multiplication. As we can see from this Java code, that is, this S means single precision. So this is float in Java, also the float in CPP. So you can see that this is the source code or some of the basic code for implementing HGEMM. So that is for ij, that is belong to M, and j belong to N. First we calculate the sum, that is sum equals to aik times bkj. So we can recall the figure before. So that is we need to choose the I from the M and the J from the N. That is this part. And then this part equals to the whole line of A times whole line of B. So the formula listed here in your linear algebra class have shown that the C, the result Cij equals to sigma AIR times BRJ. That is the sum. And because the GEMM API needs to times alpha and beta, we put alpha and beta here. And the C code here is also the same. Oh, and after from the single precision general multiplication, we also have the double precision general matrix multiplication. That is changed from float to double. Now, since the GEMM's API is too complicated, in this competition, we only require you to use this simplified HGEMM. That is, for example, you can only calculate C equals to A times B. You don't need to calculate the alpha and beta and other things. You only calculate this one. And the source code will look like this. So that is for anything that belongs to M, anything that belongs to N, that is Cij, and any of the results matrix that equals to Aik times Bkj. Well, as we introduced before, we introduced float and double. So here you may wonder what's the difference between float and double. And here I will have to recall some of the knowledge you learned from the computer organization. That is the floating point standard from IEEE standard 754 in 1985 proposed. So as you can see here, you can see some of the floating point, how the floating point represents in the computer memory. Like here we got a formula here. That is, for example, we have learned before a float is 32 bits inside the computer memory. And for the first bit, it was a sign bit. That is, 0 means greater than 0, or greater or equals than 0. 1 means negative. And exponent means the here we got the 2, and we can have use the exponent minus bias to get a number. And then we got a fraction. The fraction bit will plus 1 and times to the exponent value, and then get the final result. And let's get a simple experiment or simple lab from here. And I will show you how to calculate or how to represent the floating point in the real world. Okay, so this is the IEEE converter. Now I want to represent anything. For example, let me give an example like here. What are the other examples? Okay, let's give this exercise as an example. That is how to translate 25.5 in FP32. And this may be easy. So for 25.5, that is greater than 0. So its sign bit is 0. Now, for the exponents, we know that since it's greater than 0, and 16 is less than 24.5, but the 32 isn't. So which may be, we should put the exponent here as 4 times 4 at 127 as the formula here described. That is the bias. So that would be 131. 131. Here we got the exponent. Now we need to get the fraction bit. So since here we got 16 and we got 1 before, so the value stored here is 16. And then we need to get to 24. That is, we need to add 8. Okay, so we can see at the end. And then this one, since this is 8, this will be 4, and this will be 2, 1, and 0.5. So here we can successfully representing the 24.5 in FP32 using this storage. And the binary representation as this series of 0 and 1, they are the actual numbers that store in the computer memory. And saying of that, we have introduced like FP32, how to represent numbers and floating numbers inside the computer. Now I would like to introduce FP16, that is half precision. And here, as you can see, the half precision you also use a sign bit, but using less exponent bits and 10 bits of fraction bits. So we can just change to FP16 and try to like represent, okay, so it will be the same. Yeah, you can see that first is still 16 and adding 8 4 to 1 and 0.5, that would be still 24.5. So as you can see, one of the benefits we have gained from this FP16, that is, we would not change most of the bits, and it will represent the same value. And it only caused the fraction bits to slow down, and also some of the bits that is lower down. And for what benefit why we are using FP16? First of all, for HPC, it will not be a good idea, because HPC, for the scientific computing, you need to represent some of the physical value or some of the real world value as precise as you can. But FP16 use less fraction bits and less exponent bits, which would let some of the information lost, so it will not represent much of the thing. But for the LLM inference or the LLM training and LLM, since we have found that most of the parameters, they doesn't need so much of the number range. Also, it did not need so much of the precision. So we can only store store most of the LLM's model information with half of the memory. Here we can do an experiment from the Hugging Face. For example, we can see there is a model here, the Cream 0.6b FP32. So how much does it cost inside the memory? And since it's 0.6b, that means it has 0.6 billion parameters inside the model, and all of the model's parameters are stored in FP32 version. So for FP32, that is 4 bytes, and which will cost 4 times 0.6 billion equals to 2.4 gigabytes. So it will cost 2.4 gigabytes in memory. Let's see the file if we are right. And that's it. This is the model safe tensors. You can see this is 2.38 gigabytes, which is close since of the binary representation. So this will be the real, the model would occupy the memory. Now let's see some of the other things models. Let me think. Also 0.65. What do we have? Okay. So let's see. You can also see from here. This model card here shows that it has a BF16 stored in tensor type. So for BF16, the 16 means it is 16 bits, right? So that is 2 bytes for parameters. So that is 2 times 0.6 billion. That is 1.2 gigabytes. Let's see what happens. Model safe tensors, 1.5 gigabytes. As you can see, they are all Cream 3, but since they are storing using the different tensor types, you can reduce most of the memory from it. And as you can see, nowadays most of the models are very, very big, like the DeepSeek V2. It contains 671 billion parameters. That is very, very big. So by using like a FP16 or even FP8, you can only store all the result and put all the model inside the GPU or even on the CPU memory. So as you can see, the HGEMM most of the time is running for the inference or the LLM's training. Or so this matrix multiplication is only for the AIs nowadays. And inside CPU, I will also introduce using the parallelization technique, that is using OpenMP. As you can see, after adding one line of the, as we shown here, that is programmer OMP parallel 4. And by doing that, you can calculate the matrix multiplication with multiple threads, as we can see here. This is a single model of our CPU and our memory. And here I will introduce another technique that is called matrix tuning. So the idea is that originally our writing code is like we are fetching of the numbers like this one, that is fetching a row in the A, then fetching a column in the B, fetching a column, fetching a column, fetching a column. However, in the real world, we have a cache inside our CPU. And if we learn the computer organization, you will know that the CPU will load the data that is near inside the memory to the cache. So this happens that if we just analyze this program, we will find that the memory access pattern inside this program is not efficient. You can see if we just like we get one line inside and then we access this one. However, we will find that when we access to the next line, next row, since we haven't get this row before, you get a cache miss. That is pretty wrong. But one solution is matrix tuning. That is, we only fetch part of the matrix first, and then calculate the result, and then store it, and then calculate the others. And this technique would be good since you would reduce most of the cache and try to fit all of the cache inside the higher level cache. So utilizing the memory access pattern will raise the cache hits and closer and with higher. Here I would do the second experiment using the perf. Now I try to analyze the thing using perf. Please wait a second. Okay, so here we comes to the lab 02. And here I would give you like one function. So as you can see, the first function here, that is HGEMM, and it would be the very simple, that is for I equals to 0 and for I equals j equals to 0, and then calculate the sum. And another thing is the tuning. So here this would be the tuning. I would, as you can see, each of them will add to one at a tile. The tile means one block inside it. And then inside one of the block, you calculate the computation. Now, for these two things, I would help you to see if what's the difference between the two algorithms. To perfect that, I would introduce you to the perf. So as you can see, perf is the Linux tools that can help provide your program. Like here we are profiling using the D cache loading, last level cache loading, and the load L1 cache misses and the last level cache misses. Oh, by the way, let me just recompile the program again. Okay, and here we try to profile. Oh, sorry. Okay, so as you can see, the D cache loading is like 9 billion, 9.9 billion load times. And the last level cache loading is about 1.7 millions. And let's see what happens for the original program. That is the trivial program. Like here and here we do. Oh. Now we're using the curve. See what happens. Now, as you can see, compared to the Turing that is optimized algorithm, the most difference here is the last level cache loading, right? You can see here the last level cache loading is raised about 1 billion. So this will be cause a result that the data would store in the last level cache, but not in the higher level cache. This will cause the latency, right? The latency would rise since as the cache that is far away from the register inside the compute cores. So you can also see that here for the first optimized program, it costs only about 2.8 seconds, but the second one costs 5 seconds. So this will be our simple experiment to show that utilizing the memory access pattern, it will help raise the cache hit ratio and in a closer place. Now here, since most of the students didn't learn operating system before, I will only show a program here. Since every time the program want to fetch the data, it will translate from the physical address to from the virtual address to physical address. Here we also got a TLB translation here, and sometimes this TLB will be also a bound beside L1 cache and L2 cache. And to utilize memory access pattern, and we can also see some of the papers also using these ideas like power infer. Here in this paper, they find that for most of the LM's models, only about 20% of the parameters inside the model matrix are activated. So their idea is like we can put this hottest model or hottest neural inside the GPU, but the rest of them inside CPU. The result shows that if we put this, we can only put about 20% of the neurons inside the GPU, rest of them in CPU. So our GPU can run a bigger model, even if the model size is even larger than our GPUs. We can still run it and compute it. So this paper's its title is Fast Language Model Serving with a Consumer-Grade GPU. That is, try to run a bigger model inside your 4019 or other 4090 or other GPUs. Now, let's keep on. The other optimization is using the SIMD instructions. And in the 1970s, some of the scientists proposed this instruction models, that is SISD, single instruction, single data. And SIMD is one of them, that is single instructions, multiple data. That means you can only use one instruction to compute one vector things. And so our HGEMM kernel can also use that to calculate. And this time you would boost most of the computation time, since it was done on the hardware. And to learn more of them, you can reference to the Intel Architecture Software Developer manuals. And another technique is to loop unrolling. Here, if you learn the computer organization, you will remember that. So since before that, if we just compute one line, and then you will find that you will compute the for k equals k if k is less than the big K, and which would cause that most of the CPU cycles are doing the for loop, but not the real computations. So by adding more of the computations and utilize the registers, you can help improve the computation ratio and help improve the computation speed. Now, let's go to the second part, that is, what is CUDA? And CUDA is a developed environment for creating high-performance GPU-accelerated applications. And that is nowadays we have many applications like a graph, machine learning, deep learning training, and deep learning inference that is using the CUDA. So when they are trying to use the GPU resource to compute, CUDA will provide developed environments like giving, also writing the CUDA code and that is running on the GPU and help accelerate the computation. Now, what's the difference between GPU and the CPU? As you can see, CPU may be using most of the cache and the cores and the control layer, but the GPU, they want to use many of the cores to compute. And here inside NVIDIA's instruction book, it defines CPU as a host and the GPU as a device, and connect them using multiple interconnect lines like a PCIe. So when a CUDA program was running, first the host was running on CPU, then it was running on the device that is in GPU. And then after the kernel, here you can see if we want to run the GPU code, you need to launch a parallel kernel. And I will introduce this kernel later. And then after this kernel was executed, it will back to the CPU and do other things and then run other kernels like this. Now here I will introduce CUDA using a simple CUDA introduction. So here you can see this is a very simple HGEMM kernel. And let's go back. First, you will initialize with MNK and initialize 3 metrics. And then you try to compute, initialize them. And the CUDA malloc means to try to malloc some of the metrics that is on the device with size A. And then so CUDA malloc means you need to ask GPU for a memory block to store data. And then CUDA memory copy is API that you can copy the host device data to the GPU, to the DA. And using like a CUDA memory copy host to device. And then after copying A and B, you can begin to do the computation. Now here we come across 2 things, that is block and dim. What is block and dim? And that comes to our GPU hierarchy. So since we got many threads, that is much larger and sorry, not larger, larger amount, I would say. That would be larger amount of the thread. It will be difficult to manage this thread in GPU. And the NVIDIA to try to control and manage this thread with 3 levels. The minimum level, that would be thread. And then that would be the thread block. After thread block, you'll get a grid. That is 3 levels, thread, block, and the grid. And so here you can see this block will be the minimal number. And then it would be like a 16 times 16. That is, each block is having 16 times 16. That is 256 threads, and that would be like for example, this is 1024 divided with 16. That would be 32. That would be 64. So there will be 64 times 64 equals to 4096. Yeah, that's right. Sorry, let me change it for this computation since we are using like yeah, that's right. And let me just delete it. Okay. So here we will got 1694 thread block, which would be much larger for one CPU, for one thread, right? And then we will launch the GEMM kernel. What is GEMM kernel? Let's go to here. So the global means this code will be happens in the GPU and the CPU, but that will be okay. And first you need to compute the block index and the block dim, adding thread index, and compute the curl index using this. And then for each of the thread, you need to compute this one. That is the key. So here, each thread is helps to compute theCij's result, right? As we've seen before. Okay, so yeah, by doing that, you can see how fast is the simple GEMM. Oh, that is so fast. You can use the time to see how fast it is. That would be about 0. About 300 microseconds, I would say. And if you see our lab 2's data and the time, which will be about 2.8 seconds. That is much slower, 8 times slower than the simple GPU code, while the GPU code can be even faster. And, so thread, block, and the grid will be the virtualization in the software, while in the hardware, they are implementing using CUDA core. So for one CUDA core, that is one-to-one correspondence to the one thread, and one SM that will correspondence to the one thread block, and the one device that is correspondence to the grid. Well, there is a hard point that is inside each of the thread block, the GPU manages all the threads using a WAP. And this may be some of the hardware issues, and that will be deeper. If you are interested, you can explore more inside it. Now, the GEMM in CUDA looks like this, as we shown before. That is the A and the B, and then that will be compute. And you can also do the matrix tuning inside the CUDA. So since all of the compute model are all the same, since you also got the memory in GPU and the compute unit in the GPU, so you will also get the cache miss inside the GPU, or you cannot just load off the data inside the cache. So tuning in CUDA will be also effective. And another thing is loop unrolling in CUDA will be the same as the CPU shows, since GPU don't need to calculate like the for loop. Now let's see. You can also take a reference from the NVIDIA's white paper book. That is, look up how many threads you can get and how many grid you can get, how many block you can get. Here we can see Tesla V100 with 80 SMs, that is 80 blocks. And inside of each box, there will be like everything is a FP32. That is okay. Since when in the computation, FP16 will be computed using these cores. And you can also see there will be tensor cores inside the Tesla V100. Now, to introduce the tensor cores, I will tell you that tensor core is increasingly integrated into modern high-performance processor to enhance matrix multiplication performance. That is, although this FP16 for FP32 is very important, people find that most of the computation are still doing the matrix multiplication. So they try to invent tensor core to do the matrix multiplication. And what can the tensor core do? Let's see the PPT, the slide here. As you can see, for each tensor core, it can complete a single 4x4 matrix multiply and accumulation MACC in one clock cycle. That is, doing the matrix B times matrix A plus matrix C equals to D in one cycles. But how about in CPU? Let's imagine. For example, if you want to calculate the Z00, you need to calculate A000123 times B0 123. That is like uh 4 multiply and then add 1. And also you need to add all of them. So that would be 4 multiply and 5 addition to get one thing. And that would be like 9 cycles. So for the 16, you need to like do all the things in about 9 times 16. That would be like 144 cycles for calculate this 4 times 4 matrix multiply and accumulation. But tensor core can only finish it in 1 cycle. That is tensor core speed up. And the figure here shows how tensor core computes. Also, tensor cores can compute many of the compute things, like the FP16 and TensorFloat 32, FP32, and the BF16. Now, I would introduce tensor core using a single introduction. So here, before the GPU computing, everything remains the same. That is copy and the initialization copy, and then make sure the grid and block. And let's see how the GPU computes. So this will be the GPU launch kernel. And here after index calculation, now here is the thing. Since tensor core is one special unit inside one of the SM, so you need to initialize the thing you want to compute in tensor core using the WMMA API. And for the rest of the API's knowledge you can learn from the book, it is okay. And the accumulator here means the matrix C here. And matrix B means the B here, and A means this one. And this API means to fill C with 0, and then you need to like compute the C starting address. That is, for every tensor core, you need to since every block got one tensor core, and you can let one block to manage one tail, and for one tensor core. That is, after getting the starting address of A and B, then load the data using WMA, load to the tensor core memory, and then use main and A synchronize. That is a synchronization compute API to compute this matrix multiplication and accumulation, and then you can store it back to the your result flow C. That's here, and we can compile it. So here I init the matrix with the size of 1024, 1024, 1024, and then the matrix A is 1, and the matrix B is 2. Wow, that's very, very fast, right? That would be even faster for the 0.338, faster than the. Yeah, I think most of the time they will be much faster. And since this tensor cores, I haven't get most of the optimization. I just show a demo here. You can optimize it later. Here I show most of the reference here. You can just click it and help to optimize your result. Like this paper. This paper is from IPDPS 20. This is an old paper, and its idea is to squeezing the operator performance using tensor cores to optimize HGEMM, right? A half precision matrix multiply. And you can get some of the idea here to help how to optimize your program. And you can also see some of the analysis here. And here I have just introduced it before. And also I would introduce how CUDA code and WMMA code works. So after writing your CUDA, you'll be compiled using MVCC, and then you will compile it into an IR code. It's called in parallel thread execution code, the PTX code. Then during the runtime, since different GPU have different architecture, like the V100 is that is uh, uh, that is Volta, and T means Tesla, A means Ampere. So that will be most of the machine that will be have most of the machine structures. So for the different machines that will compile into different specific machine codes. This is called the SAS code. After the execution, the SAS code will be executed and scheduling using a hardware scheduler called WAP scheduler. And as we learned before, that is the minimal scheduler for thread management in the GPU. And here you would like separating the several thread group and segments and to compute them step by step. And for the time reason, I won't go deeper into this one. Now let's see some of the idea. Nowadays, people are trying to using tensor cores to accelerate most of the scientific computing, like the COMP stencil. This is one of the best paper from PPOPP 24. That is transform stencil computation to matrix modification on tensor cores. So the idea is, if we want to solve these equations in the physics, in the traditional science, computer science, we will solve them using that is FDM, fractional differential method to compute the equations. And here I write a Python program to simulate this. So each time the new grid equals to the old grid with this temperature. And then after running several grids and several iterations, you can see the time is spreading to the central units here. So here we're trying to using the CPU or the computer to simulate temperature spreading in some of the environment. Now their idea remains the same. They find that these computation patterns may remain very, very similar to the convolution inside the tensor core. And also that is its pattern is very like to the convolution. And also for the convolution nowadays, we have many techniques to accelerate it, like using image to code technique to translate the convolution into the GEMM. So this paper's idea would be like would be very familiar. So here, since this convolution can translate into the GEMM, how about translating stencil into GEMM, then compute in the tensor core? So this is this passage idea. For the rest of the passage, you can refer to the paper. Now, let's come to the third part, that is how to profile program. So the normal CUDA function run like this. So after user gets an application, then you will run on the GPU with integrating with CUDA driver and the CUDA runtime environment. And to profile it, you will use the Nsight compute integrator and the profiler that will look up the application when during the runtime and get some injection in it. Now, there will be two programs. The first program is NSYS. That is a system-wide performance analysis to visualize an application's algorithms. And the second one is the NCU that would see some of the operators' performance inside one of the inference or other GPU work. Now let's come to the lab here. So here for the lab 5, I was still giving this GEMM kernel with 10240 and 10240, 10240 computer sensing, and the TCU also doing the same thing as before. Okay, so first we can try to like for this one. We can use this thing. So that is nsys file. Oh, sorry. Yeah, you would see some of the command here. And let's see profile. Yeah, you can see most of the API here, and you can start some of them by reading this API. Here we are using NC profile. Yes, equals to true. So here you can see it's starting collecting the data, and it comes out the same result. And you can see a lot of results come out. Oh, sorry. To see it completely, you can download this repo here, and then open your nsys inside your computer. If you don't know how to download it, you can search on the internet for NVIDIA Insight system. This will be simple. And let's see what's our report here. Oh, that will be here. And we can open it. Here we can see how our GPU is running. So it will show some of the our runtime, what function is calling, like the CUDA, copy, and other thing. And here we can see one of the kernel summary, that is the GEMM kernel. Wow. So it shows that our GEMM kernel costs about 3.7 seconds. That would be a little bad. And yeah, that would be too bad. And what's happening? I think one thing maybe like we are scheduling too much of the grid. You can see that is 60-40, 60-40, 60-40. Since having too much grid or too much good block may get over scheduled and overhead inside one of the GPU. Let's see if we can profile it. Let me think about it. Okay, here, let me think. Decrease, so then let's see what happens. First, we can compile it. Second thing would be like profiling. See why there are too many functions. What's this kernel causing? Wait, and open. Oh, this is very unlucky. Wow. Wait, why there is 1000? That would be pretty bad. Oh, I'm so sorry. Uh, that would be my problem. My bad. Then it's not 8, we need to like 32, right? Okay, let's see what happens now. Okay, the result. Things looks a little better than before, right? Since here it is ended at 3.2 seconds. And oh yeah, here you can see after some getting lower than the grid, you would only have 930 microseconds, but this one's gets about like 3.7 seconds, right? We get 3 times faster. Yeah, that would be very cool. So this is the N6, and as for the NCU, it will be the same. And here but since the time is limited, I can only show you some of the results, like here. Oh, let's see. Why we didn't have yeah. Oh, sorry. It will be like here. Yeah, and to see how your CUDA program was run, use NVTop. Here, this is the GPU's computing, and the yellow one is GPU memory. And you can see your program here running. Now let's get back to the Nsight. So Nsight is a system that can see much of the thing in a deeper and a lower bound way. And where is my NCU? Yeah. So here this is your GEMM kernel, and you can see your compute throughput, memory throughput, and how many registers you are using per thread, and your grid size, how many grids, and you can also see even your source file. That is the SAS code we introduced before that is running on your GPU. And here you can even see the throughput here. That is the computer SSM and the memory SM. The result shows that it only contains about 35% of your throughput, but the the good result will maybe about 80s or 80s. So this may be not very good. And this will be the roof line at here. So what's this like? This is the double roof line, double precision, but this will be the single precision. And since we are doing the FP32, and we may not have the FP16 operator, our original arithmetic intensity will be go to like here in the middle of this big line. That would be the most of the good. That means we still have many of the optimization rooms, right? So here I will introduce the SAS code and PTX code. That is some of the MVCC CUDA code that will be translated into PTX code here and then translate to the SAS code. Well, you can also add some of the PTS code during the CUDA programming that would sometimes increase your performance. Now let's give a brief introduction to the compute intensity. So here we define pi as the maximum flow per second that one GPU or one device can compute, and the beta means the maximum memory access per second. Then the compute intensity equals to Imax equals to pi divided beta. And by doing that, we can draw a line in during the performance. that is how many flops you can compute per byte per second, and how many intensity you can gain, that is by loading 1 byte, how many flops operations you can do. And this point will be the Imax, that is compute intensity optimal. And the beta here, since the performance equals to the bandwidth times compute intensity, so when the performance divided with compute intensity, that will be the bandwidth, that is the beta here. So when you are in this triangle area, that is range from the red line and the x-axis and this Imax axis, and this time it will be compute bound, since you find that, hey, originally I can do like the sorry, yeah, let me just go introduce it inside it. And originally you may can like compute at this point, but if you can only compute at this point, that means some of the compute resource you didn't utilize them fully, since the memory loading may be too slow. So or your compute or your algorithm didn't utilize the bandwidth very well. Well, here in the compute bound, you can see that you may utilize the memory very, very well. That is loaded very, very fast. But the performance, that is how many bytes you can compute, doesn't show very well. It seems that you are not using the very good computation methodology. So this line against our roofline models. And here, another representation of the roofline model is using a linear line and two linear lines, but one is represented with the peak flows, since like for A100, you have a peak flows here. That means how many flops all the core units are computing and how many flops you can get. And the DRAMs here means your throughput inside your GPU memory, or your CPU memory, and they also form a line here. And all of your program's performance lies in this triangle and this rectangle. And in the triangle, you will be memory bound. In the rectangle, you will be compute bound. And there will also be a hierarchical line. That means, for example, in this figure, you can see different memory, like L2 cache and DRAM cache and the DDR. So since they have different throughputs, their linear line will be different. And you may answer, hey, I thought that you just draw the line at the start of 0, since this k must equals to the bandwidth, right? And you can also define a point using the Imax. The result here, as you can see, this is also not points to 0 and not points to 0 because they are taking the log. And you can see the below figure here. Yeah, you can see like the DRAM and L2 cache, but the 0 here doesn't mean the real 0, but means the 2 to 0, right? That's 1, right? And you can't point to 0. So, but they still hold the same tendency. And you can see by computing the tensor core, since tensor core can get a much better performance than the FP16, that is not very good cores. And you can see the level line will rise up, and the cache line, since the L2 cache may be faster than the DRAM, and the line will also rise up. That means the K is bigger, right? And yeah, that would be another examples. And here I would introduce another paper for you. And here, so its idea is it is also finished. It is also analyzed their systems that is called Ascent, that is in Huawei, using the roofline model. But they find that before that, all of our computation was like loading from memory, then compute, or like loading from DDR, then the loading to the L2 cache, and then compute. So the compute may be limited to the minimal bandwidth between DDR and L2. But here you can find that this is the architecture of the ASIN architecture. And when they are loading the data, they can load the data to L0 and L0 and L0B, L0A in parallel. So for the naive instructions or the previous roofline model, they can only load the data into one register, and you cannot control L0B with any loading instructions. And the roofline will be limited to L0A and L0B. But here, since you can load it in parallel, you will find that the actual performance can be scanned up after the loading. So, and also you can see that the compute core here can also compute both of them. So their idea is very simple. They find that the analysis of the naive roofline will be incorrect. So they just load it in parallel and do a new model analysis, and then they are trying to load them in parallelly and bridging the gap and get a better performance. That is the Aspolo's 25 ideas. Very simple, right? And yeah, and there will be a lot of model to analyze your program and with your profilers and other thing. LogP is also a framework, but you can learn it with some of the slides over the link. And I haven't talked about more of the high-level technique here, since I think this computation would help you to learn more about this technique, like using the shared memory in GPU, utilizing some source code in GPU, and solving the warp divergence and warp bank conflict, and also trying to use some technique like a double buffer. To learn this thing, you can reference to some of the white paper architecture and some of the blogs inside the internet. And I think you will benefit a lot from your technique and your learning. And here we would like to introduce you with some of our competition details. And as you've seen before, if you can click here, and you can see the title here, and this will be a CPP review video if you learn some CPP before but you forget. And this one is like here, as I can say, you only need to compute this one. C equals to A times B, and here our score will be measured on this 10 case. And you can use our Python program to generate the random results of this test case. And here you can also try to maintain a structure of your code using like a blocks. And you can explore what blocks are constructed. And another 50% of the score will be from the technical report. That is like how you use your tensor core and how you utilize your optimal instructions and other things. And this will be your scores for the 10 test case. And you can define some of the things here. And here I give you some advice. And this is something you should submit to me. And yeah, there will be other advices and references. That would be all. Yeah, and that would be today's learning courses. And thank you for your listening. If you have questions, feel free to reach out for me. Thank you.